Hey guys, I'm Siddhant from Microentu, and today we'll be discussing about aging. And in this video, I'd be discussing about why we age, what can we do about it, and some things I would like to tell you that you can do as of now to increase your lifespan without any medicine. And other than that, we'll be discussing a little bit about reverse aging. Okay, so in this video, I'd be mostly talking about cell senescence, and other than that, we'll be discussing about loss of information in the epigenome. And also, cell senescence may be caused by this loss of information that we'll be discussing in the second half. Okay, so first off, what is cell senescence? Cell senescence is a state where the cell you have when its DNA has been damaged to the point where it's not functioning very well, then it has two options. Either it can go through a programmed cell death, which generally most cells go through, if that's the case with them, and if not, what happens is they become zombie cells in a way. So senescent cells are cells which do not care about their surroundings. Like, let's say you have a liver cell, so it's supposed to contribute to the tissue, but when that cell goes senescent, it's not doing that. Other than that, it has pro-inflammatory, it releases molecules outside to other neighboring cells, which make them senescent, and they also cannibalize on other cells, so to use their machinery. So that's why they are called zombie cells, and it can be caused by multiple reasons. Cell senescence. Few are decreased sirtuin levels, mitochondrial dysfunction, and mostly DNA damage. That's the primary cause. And even in that, mostly we have seen that telomere shortening is one of the major contributors in this DNA damage. Okay, so let's start with telomere. What are telomeres and what is telomere shortening? So telomeres are the very at the end of every chromosome. You have this set of TTA triple G sequences that are very long, and what they do is they are like the ends. You can think of them like the ends of a shoelace. So they are there just for protection, to just say like when DNA replication takes place, it's like telling the cell that okay, you don't have to replicate any further. And also it acts. It also does not let the very end of your chromosome get attached to anything else, or let's say any other part of the DNA or any other chromosome. Okay, so these are what telomeres are. Now the problem with telomeres is that they get shorter and shorter as they replicate. So let's say you had a cell initially which was very young, so it had a nice long telomere, but after quite a few replications, this telomere length shortens. So the number of times a cell can do that, the number of times it can replicate before the telomeres reach the point where the DNA damage is so bad that it cannot replicate any further. That point is called the Hayflick limit, and generally for cells it's between 50 to 60. So after let's say 60 replications, your cell, it cannot divide anymore. So generally what happens is that they go through apoptosis. So apoptosis is a fancy word of saying programmed cell death. So in that, components of the cell are used by the rest of the body. But other than that, the other thing that can happen is senescence, as I described earlier. So now the thing is, what we can do is either flush out these cells, or else we can maintain the telomere length they have, so that they don't go senescent in the first place. So what we can do, the first thing we can do is maintain their telomere length. So that is by telomerase. So telomerase is an enzyme which does this job. It keeps the telomere length constant. And but the problem with telomerase is that it's found in two places mainly. So one is cancer cells, and the other is stem cells. So the cancer cells, because they have telomerase, they can divide indefinitely, and they do not go senescent. But the problem is, even though they are found in stem cells, the bigger problem is they are found in cancer cells. So the thing is, if you use telomerase, the chances of you having cancer get higher, so it's a riskier thing to do, but still it's something that can be done. But I would say we shouldn't look forward to it, because it's like a double-edged sword. It's good, and on the other hand it's also bad. You never know. So that's all about telomere shortening. And then what we can do, the other thing that we can do, that is to flush out all these senescent cells that we have, rather than just keeping keeping the DNA healthier. We can just flush these out, so that there is space for more of the other cells that can do the same job and contribute to the body, rather than just eating other cells around. So this is done by senolytics. So these are a set of drugs that do this job to flush out all the senescent cells you have in your body. Not all, but they try to get most of the senescent cells, and most of them they have side effects, but mostly we are not trying them on humans, no, at least not yet. So the one I'd be talking about is the FOXO4 DRI, that's in front of you as of now. So this is a protein which is actually made by a gene called FOXO4. That's hence the name FOXO4 DRI peptide. So this is translated by the FOXO4 gene, and then what it does is, with the P53 protein, which is responsible for maintaining the cell cycle, apoptosis and DNA repair. What this does with P53 is that it will penetrate the senescent cell, go inside and make sure that the mechanisms that are keeping it alive, they don't work anymore. So that now the immune cells in your body, they can take out all the components inside and use it for the better good of the body. So these are senolytics. This is only one of them. There are multiple. Okay, so let's go ahead with the second part. So this is all the talk about epigenetics, where I would like to show you how loss of information takes place in cells, and how that makes us age. Okay, so before I begin, I'd like to set a good analogy, that is, if you don't know, I'd like to tell you here, is that your body has millions of cells, actually trillions of cells, and each of them has the same set of DNA. So information in cells inside your body, it's maintained in two ways. One is your DNA, right, and the second is your epigenome. Okay, so you can think of DNA as like a huge library. Okay, and each cell, let's say you have a skin cell, maybe a liver cell, maybe a nerve cell, each cell has to just read a certain part. So if it does not read that certain part and reads, let's say, some other part, then it's not doing the job it is supposed to do. Let's say if you are a nice liver cell, you should stay a nice liver cell and not read other books in the library. Okay, so now this library, the amount of restriction and the amount of relaxation inside the library is maintained by histones and a few other proteins that maintain the packing and unpacking of the DNA around these histones. Okay, so histones, simply put, they are like places to bind your DNA. Like it's you can think of it like how you roll around a fire hose, right? So here the DNA is the fire hose, and the histones are the thing on which you are tying the fire hose. Okay, so the amount of packing you need in cells is enormous, and that is because each cell you have in your body, because I cannot even, it's inconceivable to tell you how small a single cell is, and in that single cell the amount of DNA you pack is 3 meters long. So it's even longer than most people's height, right? And for just to let you know, if you take out all the DNA you have in your body, entire body you have, and spread it out in a single line, you could go from the earth to the sun and come back 600 times. Okay, so that's a huge number. So you need a lot of packing. So for that we have histones. Okay, now histones can pack the cells in two ways. One is quite relaxed, and the second is not so quite relaxed. So the relaxed one is called euchromatin, in which there is quite a bit of open place for the DNA, and the other is called heterochromatin. So that's really tight packing. Okay, so if you can switch between these two, you can let the cell know what parts of the DNA you have to read. Because if it's packed too much, the cell won't read it, and if it's packed too less, then all the genes will be read. So you need to maintain that perfect balance, so the right books are read from the library. Okay. So this balance is maintained by adding and removing acetyl groups. So if you add acetyl groups, what they do is relax the chromatin. So if you have, let's say, a heterochromatin, it will become a euchromatin if you add these acetyl groups. And this thing, addition and acetylation and deacetylation of histones, this is achieved by sirtuins. So sirtuins are a set of genes. You have 1 to 7, SIR 1 to 7. So what they do is they maintain this acetylation and deacetylation. Few of them have some other jobs as well, but mostly, as you can see here, so 1, 2, 3, 5, 6, 7, their job is acetylation and deacetylation. So now, if we can maintain this acetylation and deacetylation, your epigenome, the part of the external part of your DNA where this reading is done or not done, this is maintained. So let's say you have a liver cell, and your liver cell is working all fine, it's not reading the wrong genes. But eventually what happens is, after quite a bit of damage that's been done to your body, to your cells, what happens is that the wrong parts of the library are starting to be read. And that is because these sirtuins, the set of genes that translate the protein that maintain this acetylation, deacetylation inside the cell, that has reduced. The amount of translation of these genes, of these proteins, has been reduced. Okay, so that's one of the reasons why we age. Okay, and one more thing, there are two other genes I'd like to talk about. One is mTOR and the second is AMPK. So mTOR, it looks for the amount of amino acids you have in your body. So let's say you had a chicken 5 minutes ago. So you have a lot of amino acids. So amino acids are like smaller parts of protein, like they make up a protein. Alright. So if you have a lot of amino acids in your body, then the body is not supposed to go on with its defense mechanism to repair the DNA and other things. And the same is with AMPK, but AMPK looks for the concentration of sugar you have. So if you have a lot of sugar, then the amount of defense mechanisms that are active, it's reduced. So that's the thing, that like if you eat too much protein, then you will age faster, and if you eat too much sugar, you will age faster. That's something you see, like it's common advice by all doctors, right? So this is one of the reasons why. Okay, and next thing I want to tell you is what can we do about this, right? This epigenetic noise, the wrong books being read from the library. We want to maintain this, all right? So what we can do is these sirtuins that I said, as you age, they become less and less abundant, and like the functioning that's reduced. So the first thing I want to tell you is that the protein alone does not just the protein alone, certain proteins that are translated, they don't just do the job. You need another molecule called NAD+, which binds to the protein, and then only your acetylation and deacetylation is maintained. So if you don't have that NAD+ molecule, then the sirtuins don't work very well. So what was done was an experiment in which a mice, an older mice actually, that mice was given NMN. So NMN is a molecule which the body can use to make NAD+. So NAD+ then combines with the sirtuin proteins, which maintain acetylation, deacetylation, and due to which your epigenetic noise is decreased, better cell repair, better DNA maintenance, and hence the cell you have stays the way it is. And this is very necessary if you think about it. Like, let's say you had a liver cell. So let's say that liver cell became like 90% liver cell and 10% a neuron. Okay, that does not sound that bad, but think about this. If you have a nerve cell, a neuron, and that became 90% neuron and 10% liver cell, that does sound bad, and that's what we want to prevent. So this is what they did. They gave these mice NMN, and NMN made that NAD plus, which in turn created a chain reaction in which you get better DNA maintenance, and hence they were able. They grew more hair, they ran more faster. So this is like, you can think of these the age of these two mice as like one being 70 in human years and the other being 20. And the ones which were given NMN, they ran 3 kilometers. So that's like a marathon. That's like an ultra marathon for mice. They don't do that. They don't run that much. Okay, and that this was with older mice, not even younger mice. Okay, so this is all about the epigenetic noise and what we can do about it. So these are some experiments that are being done, but they're still not being done on humans yet. But people are looking forward to it. The researchers are all right. So now what we'll be discussing is reverse aging. So reverse aging, I would say, is something that we've heard about, but it's not being talked about much in like the general public. People don't believe it that much, but this guy right in front of you, he I would say is the person who might be the key to reverse aging. Okay, so the person in front of you as of now is Shinya Yamanaka. So he's a Japanese researcher who won the Nobel Prize around 2012, and he won the Nobel Prize because he found 4 genes in the human genome, when activated, get back a differentiated cell. Right, for example, when you are born, when you're an embryo, you have a lot of stem cells which then differentiate into different cells. Let's say a liver cell, a skin cell, a neuron, there are enormous number of cells you have in your body, the types. So what he did was he found these 4 genes that when you activate them, these cells you already have, they become stem cells. So it's like going back to the stage where you were born. But this is not very good if you just directly do it. So what people did was, as you can see here, there are these 4 genes: KLF4, SOX2, OCD4, and MYC. So these 4, if you use them, you can get back, if you have, like, say, a differentiated cell, you can get it back to a stem cell, which can then differentiate again to become something else. So the experiment that was done was on a mice, which it was an older mice, which had lost sight because of dead cell accumulation in his eye. So what they did was injected 3 genes via a virus. So viruses are not always bad. If you are not living under a rock, there is a pandemic going on, and that's due to the coronavirus. But viruses are simply put, it's like a box of protein in which you have a set of genes, which when they come near any cell, they just inject themselves into the cell. Okay, so what was done was these 3 genes that I talked about, which get you back to the stem cell stage. These, actually there are 4. They use 3 so that you don't get back exactly to a stem cell, because you don't want that in already mature mice, right? If you do that, then it's like a huge tumor. Rather, you wanted to get back, like, let's say, a younger eye cell, right? So that's what they did. Instead of the 4, they left out MYC and they used the 3 genes. And what they saw was that the mice they had, it regained sight. It was able to see again, and that's huge. That's literally huge. That's like the best thing I have read in like a long time, and this makes me optimistic about the future. And I also want you to be optimistic about it, right? So that's something. I actually made this video to let people know what we can do as humans, and to be optimistic of the future. And like, you might be living much longer than your parents or grandparents, right? So that's all I wanted to tell. And I hope you liked it. You liked the video, and if you did, please share it. I want people to know about all of this research that's going on, people doing so much work, right? So that's pretty much for this video. I hope you enjoyed. See you in the next one.